Hello, and welcome to the Drowsy Professor. I'm so glad you're here tonight, ready to journey back through time to witness one of the most profound and peaceful transformations in Earth's history. As you settle in, let me know where in the world and at what time you're watching. Now, get comfortable, adjust your pillows, pull up your blankets, and take a slow, deep breath. Tonight, we're going to explore a forgotten prehistoric war, not one fought with weapons or violence, but a gentle, billion-year transformation that changed the very air we breathe. Take another breath, and let's begin. Imagine, if you will, closing your eyes and drifting backward through time, floating gently through the millennia until you arrive at an Earth so ancient and alien that it would seem like another planet entirely. This is our world nearly 3 billion years ago, during what scientists call the Archean, a time when the very air itself tells a story completely different from the oxygen-rich atmosphere you're breathing right now. As you settle into this ancient world, the first thing you notice is the profound silence. There are no birds singing, no insects buzzing, no rustle of leaves in the wind. In fact, there are no leaves at all, no forest stretching to the horizon, no grass beneath your feet. The land stretches out before you as a vast expanse of bare rock, sculpted by wind and water into shapes both beautiful and stark. The only sounds are the gentle lapping of waves against ancient shores and the distant rumble of volcanic activity painting the sky with soft plumes of steam and gas. The sky above you is perhaps the most alien feature of this ancient world. Instead of the familiar blue we know today, the atmosphere has a different quality entirely, a pale, almost greenish hue that filters the sunlight in ways that create an otherworldly twilight even during the brightest part of the day. This strange coloration comes from a unique mixture of gases that fill this primordial atmosphere: methane, ammonia, carbon dioxide, and water vapor, but virtually no oxygen at all. You breathe deeply, and somehow in this imaginary journey, your lungs can process this ancient air. It feels thicker, more humid, with a metallic taste that speaks of volcanic gases and chemical reactions happening on a planetary scale. The absence of oxygen is not something you would notice immediately if you could somehow survive in this environment, because this atmosphere has its own strange beauty and functionality. It's simply designed for a completely different kind of life than what we know today. The sun hangs in this alien sky, appearing perhaps slightly dimmer than the sun we know, yet still providing warmth and energy to drive the complex chemical processes happening all across the planet's surface. The light has a different quality as it filters through this oxygen-free atmosphere, creating subtle color shifts that paint the landscape in hues of amber and gold, with occasional flashes of green and purple where atmospheric gases catch and scatter the solar radiation. As you stand on the shore of one of these ancient seas, you begin to notice that the water itself looks different from any ocean you might know. The sea stretches endlessly before you, but instead of the familiar blue-green of modern oceans, these waters have a more complex coloration, sometimes appearing almost purple or deep red in certain lights, other times shifting to browns and golds that reflect the unique chemistry of this primordial world. The water is warm, much warmer than most modern oceans, heated by the planet's still active geological processes and the greenhouse effect of an atmosphere rich in heat-trapping gases. The temperature is comfortable, almost bath-like, and as you wade into these ancient waters, you can feel their mineral-rich content. These seas are thick with dissolved metals and compounds that would be toxic to most modern life, but which serve as the essential nutrients for the microscopic organisms that call this ancient ocean home. Beneath the surface of these warm, metal-rich seas lies the true heart of this ancient world, a realm of microscopic life that has been quietly thriving for hundreds of millions of years. These are not the complex, multicellular organisms we're familiar with today, but simple, single-celled creatures that have perfected the art of living in an oxygen-free world. They're the anaerobic organisms, literally meaning without air, and they represent one of the most successful forms of life our planet has ever known. These ancient microbes are invisible to your naked eye, but their presence is everywhere. They drift through the water column in vast numbers, creating subtle shifts in color and opacity that hint at their enormous abundance. Some cluster together in thin, mat-like formations on the seafloor, creating the planet's first primitive ecosystems. Others float freely through the water, following chemical gradients and energy sources in their endless quest for survival and reproduction. The beauty of these microscopic communities lies not in their individual forms, which are too small to see, but in their collective behavior and the profound effects they have on their environment. As they feed and reproduce, they create complex chemical cycles that transform the very composition of the seawater around them. They consume hydrogen sulfide, methane, and other compounds that would be deadly to most modern life, converting these chemicals into energy and waste products that support other members of their community. The seafloor beneath your feet tells its own story of this ancient microbial world. Instead of the familiar sand and sediment of modern beaches, the bottom is covered with intricate mineral formations created by the metabolic activities of countless generations of microorganisms. These formations look like underwater gardens of crystal and metal, with delicate, branching structures that rise from the seafloor like abstract sculptures. Some areas of the seafloor are dominated by what scientists call stromatolites, layered, mound-like structures built by colonies of bacteria over thousands of years. These ancient microbial cities represent some of the earliest examples of cooperative behavior on Earth, with different types of bacteria working together to create complex, three-dimensional communities that can persist for millennia. The stromatolites vary in size from small, mushroom-like bumps to massive, tower-like structures that rise several feet from the seafloor. Each one represents a triumph of biological engineering, with carefully organized layers of different bacterial species, each one specialized for particular chemical processes or environmental conditions. During the day, the photosynthetic bacteria near the surface capture sunlight and convert carbon dioxide into organic compounds. At night, other bacteria take over, processing the organic matter and maintaining the chemical balance of the colony. As you observe these ancient microbial communities, you begin to understand that this is not a barren or primitive world, but rather a highly sophisticated ecosystem that has achieved a remarkable state of balance and stability. The organisms living here have had hundreds of millions of years to perfect their adaptations to life in an oxygen-free environment, and they have created a world that is both alien and beautiful in its own unique way. The chemical processes happening in these ancient seas are like a vast, slow-motion symphony of molecular interactions. Sulfur compounds drift through the water, providing energy for bacteria that convert them into new forms that other organisms can use. Methane bubbles rise from the seafloor, creating a constant, gentle effervescence that speaks of the active microbial communities living in the sediment below. Iron and other metals dissolve and precipitate in cycles that paint the water with subtle color changes as chemical reactions proceed at their own unhurried pace. The atmosphere above these seas is equally active, though the changes happen so slowly that they would be imperceptible to any individual observer. Volcanic gases rise from the Earth's interior, adding new chemicals to the atmospheric mixture. Solar radiation drives photochemical reactions that slowly transform some atmospheric compounds into others. The entire system is in a state of dynamic equilibrium, with countless chemical processes balanced against each other to maintain the stable conditions that have allowed life to flourish for so long. Temperature variations across this ancient world are more extreme than what we experience today, but they change gradually enough that life has plenty of time to adapt. Near volcanic vents, the water can become quite hot, creating specialized environments where heat-loving bacteria thrive in conditions that would be deadly to most other forms of life. In the deeper, colder parts of the ocean, different bacterial communities have evolved to extract energy from chemical processes that work efficiently at lower temperatures. The seasonal changes in this ancient world are subtle but important. As the planet orbits the sun, Slight variations in solar radiation create gentle cycles of warming and cooling that affect chemical reaction rates and biological activity. During warmer periods, bacterial communities become more active, processing chemicals more rapidly and growing more quickly. During cooler periods, activity slows down, but never stops entirely. The fundamental chemical processes that support life continue at their own patient pace. Day and night cycles in this ancient world have their own unique character. During the day, sunlight penetrates the clear, oxygen-free atmosphere more directly than it would in our modern world, creating intense illumination that drives photosynthetic processes in bacterial communities. The quality of this ancient sunlight is different, richer in certain wavelengths that are now filtered out by oxygen in our modern atmosphere. At night, the absence of oxygen means there are no ozone layers to block certain types of radiation from space, creating spectacular auroral displays as solar particles interact with the planet's magnetic field and atmosphere. These ancient auroras would have been visible much closer to the equator than modern ones, painting the night sky with sheets of green, purple, and red light that dance and shift in patterns of incredible beauty. The silence of this ancient world is not empty silence, but rather the absence of the familiar sounds we associate with complex life. Instead, there are the subtle sounds of chemical processes, the gentle fizzing of reactions happening in the water, the soft bubbling of gases rising from the seafloor, the whisper of wind moving across landscapes unbroken by vegetation. These sounds create their own form of music, a planetary symphony of chemical and physical processes that has been playing for hundreds of millions of years. In the water, sound travels differently than it does in modern oceans. The unique chemistry of these ancient seas affects the way acoustic waves propagate, creating underwater soundscapes that are both alien and beautiful. The sounds of microbial activity, too quiet for human ears to detect, create subtle vibrations that travel through the water, carrying information about chemical gradients and biological activity across vast distances. As you float in these warm, ancient waters, you can sense the incredible age and stability of this world. This is a planetary ecosystem that has achieved a remarkable state of balance, with countless species of microorganisms working together to maintain chemical cycles that have persisted for geological ages. It's a world that has found a way to support abundant life without any of the complex organisms or processes that we consider essential for a living planet. The metal-rich composition of these ancient seas creates unique optical effects as light passes through the water. Dissolved iron gives some areas a reddish tint, while copper compounds create zones of blue-green coloration. Silver and other metals create subtle, mirror-like effects that make the water shimmer and dance with reflected light in patterns that are constantly shifting and changing. This is the world that existed before the Great Transformation began, a world of anaerobic peace, where life had found countless ways to thrive in an environment completely different from anything that exists today. It's a world that had achieved its own form of perfection, with biological and chemical cycles that have been refined over hundreds of millions of years into a state of remarkable efficiency and stability. But this ancient peace was not destined to last forever. Somewhere in these very waters, in communities of bacteria not very different from the ones you're observing, evolutionary forces were already beginning to work on innovations that would eventually transform the entire planet. The changes would be so gradual that no individual organism would ever notice them. But over millions of years, they would reshape the very air and water of Earth in ways that would challenge every form of life that had ever existed. The battlefield for this ancient war was not marked by armies or weapons, but by the slow, patient work of evolution, chemistry, and time. The warriors were microorganisms too small to see, and their weapons were chemical processes that operated according to the fundamental laws of physics and chemistry. The prize was nothing less than control over the planet's atmosphere and oceans, and the outcome would determine which forms of life would dominate Earth for billions of years to come. As you rest in these warm, ancient waters, surrounded by the invisible activity of countless microorganisms, you are witnessing the calm before one of the most profound transformations in the history of life on Earth. The peaceful, stable world around you is about to be challenged by forces that will test the adaptability and resilience of every living thing on the planet. But that transformation is still in the distant future, and for now, you can simply enjoy the alien beauty of this oxygen-free world and the remarkable success of the anaerobic organisms that call it home. The gentle currents that move through these ancient seas carry with them the chemical signatures of a world in perfect balance, a balance that has been maintained for longer than mountains have existed, longer than continents have held their current shapes. This is the baseline from which all future evolution will proceed, the foundation upon which all subsequent life will build. It's a world worth understanding and appreciating, even as we prepare to witness its gradual transformation into something completely different. As you continue floating in these warm, ancient waters, time begins to move forward in the peculiar way that geological time moves, so slowly that millions of years pass like gentle seasons, each one bringing changes so subtle that they would be invisible to any individual observer, yet so profound that they will eventually reshape the entire planet. You are about to witness the beginning of one of the most remarkable evolutionary innovations in the history of life, the development of photosynthesis by cyanobacteria, a process that will gradually and peacefully transform the Earth's atmosphere from an oxygen-free environment into the oxygen-rich world we know today. The first signs of this transformation are so subtle that you might not notice them at all without the patience to observe over millions of years. In certain shallow areas of these ancient seas, where sunlight penetrates most deeply through the clear, chemical-rich water, something new is beginning to happen among the microbial communities that have called these waters home for so long. A few pioneering bacteria are starting to experiment with a completely new way of capturing and using energy from the sun. These early photosynthetic bacteria, the ancestors of what we now call cyanobacteria or blue-green algae, represent one of evolution's most remarkable innovations. Unlike their neighbors who derive energy from chemical processes involving sulfur, methane, or other compounds dissolved in the ancient seas, these new organisms are learning to harness the virtually unlimited energy that streams down from the sun every day. The process they're developing is elegant in its simplicity, yet revolutionary in its implications. They're learning to use sunlight to split water molecules and combine the resulting hydrogen with carbon dioxide to create organic compounds. The beauty of this new process lies not just in its efficiency, but in its byproduct. As these early photosynthetic bacteria split water molecules to access their hydrogen, they release the oxygen atoms as waste. At first, this oxygen production is so minimal that it has no noticeable effect on the surrounding environment. The tiny amounts of oxygen that these pioneering bacteria produce are immediately consumed by chemical reactions with the iron, sulfur, and other reactive compounds that are abundant in the ancient seas. But evolution, once it discovers a successful strategy, has a tendency to refine and amplify it. Over millions of years, these photosynthetic bacteria become more efficient at their new lifestyle. They develop more sophisticated light-capturing systems, better ways of processing carbon dioxide, and more effective methods of protecting themselves from the harmful effects of their own oxygen waste. Each generation builds upon the adaptations of the previous generation, slowly but steadily improving the efficiency of this remarkable new biological process. As the photosynthetic bacteria become more successful, their populations begin to grow. What starts as a few scattered colonies in optimal locations gradually spreads to other areas where conditions are favorable. The bacteria that possess this new ability have access to an energy source that is virtually unlimited. As long as the sun shines, they can continue to grow and reproduce. This gives them significant advantages over their neighbors who must compete for the limited supplies of chemical energy sources in their environment. The spread of photosynthetic bacteria is like watching a slow, green tide gradually spreading across the ancient world. in shallow bays and coastal areas where sunlight is abundant. These new organisms begin to form extensive mats and colonies that can be seen as subtle changes in the color and texture of the seafloor. The bacteria themselves are still microscopic, but their collective presence starts to create visible effects as their populations grow and their metabolic activities intensify. The colors that these early photosynthetic communities create are unlike anything in the modern world. The ancient cyanobacteria don't produce the bright greens that characterize modern plant life, but rather a range of blues, purples, and deep reds that reflect their unique biochemistry and the different wavelengths of light they use for photosynthesis. These colored patches on the seafloor create an underwater landscape that looks like an abstract painting, with swirls and patches of color that shift and change as bacterial populations wax and wane with the seasons. As millions of years pass, the cumulative effect of all this photosynthetic activity begins to have measurable effects on the chemistry of the ancient seas. The oxygen that these bacteria produce as waste continues to react immediately with dissolved metals and other compounds in the water, but the sheer volume of oxygen production is gradually increasing. Areas around large photosynthetic communities begin to show signs of chemical changes as iron and other metals are slowly converted from their reduced forms to oxidized forms. The first visible sign of this chemical transformation appears in the form of tiny, rust-colored particles that begin to precipitate out of the water in areas where photosynthetic activity is most intense. These particles are iron oxides, essentially microscopic rust, formed when the oxygen produced by bacteria reacts with the iron dissolved in the ancient seas. At first, these rust particles are so small and dispersed that they barely affect the appearance of the water, but over time they begin to accumulate in noticeable quantities. The formation of these iron oxide particles represents one of the most important chemical processes in Earth's history. The ancient seas contained enormous quantities of dissolved iron, much more than any modern ocean. As the photosynthetic bacteria continue to produce oxygen, more and more of this dissolved iron is converted into solid particles that sink to the seafloor. This process effectively removes both iron and oxygen from the water, preventing the oxygen from accumulating in the atmosphere, while creating distinctive geological formations that will persist for billions of years. These iron-rich sediments accumulate on the seafloor in thin layers, each one representing periods when photosynthetic activity was high and oxygen production was intense. During periods when bacterial activity was lower, different types of sediments accumulate, creating alternating bands of iron-rich and iron-poor layers. These banded iron formations, as they're known to geologists, create some of the most beautiful and informative rock formations on Earth, with alternating stripes of red, gray, and black that record the rhythmic cycles of ancient bacterial activity. The process of oxygen production and iron precipitation creates its own feedback loops that help to maintain the stability of the ancient world even as it slowly transforms. When oxygen production increases, more iron precipitates out of the water, removing the oxygen and preventing it from reaching levels that would be harmful to the anaerobic organisms that still dominate the seas. When oxygen production decreases, less iron precipitates, allowing iron concentrations in the water to build up again for future precipitation events. The seasonal patterns of photosynthetic activity create their own rhythms in this slowly changing world. During periods of intense sunlight, bacterial photosynthesis increases, leading to more oxygen production and more iron precipitation. During periods of lower light intensity, photosynthetic activity decreases, allowing other chemical processes to dominate. These cycles create complex patterns in the accumulating sediments that record not just the activity of the bacteria, but also the astronomical cycles that control the intensity of sunlight reaching Earth's surface. As you observe these changes unfolding over millions of years, you begin to appreciate the incredible patience of geological processes. The transformation that's taking place is so gradual that it would be completely invisible to any individual organism living through it. No bacterium experiences any sudden change in its environment, no community faces any immediate crisis. Instead, the change unfolds over timescales that are almost incomprehensible to creatures that live for days, months, or years. The photosynthetic bacteria themselves seem blissfully unaware of the profound changes they're causing. They simply follow the biological imperatives that drive all life to survive, grow, and reproduce as successfully as possible. Their new ability to harness solar energy gives them access to an abundant and reliable energy source, allowing them to thrive in ways that their ancestors never could. They have no awareness that their waste product will eventually transform the entire planet. The other organisms in these ancient seas continue their own lives largely unchanged by the gradual increase in photosynthetic activity around them. The anaerobic bacteria that have dominated these waters for hundreds of millions of years continue to flourish, following the same metabolic pathways and life strategies that have served them so well for so long. The chemical changes happening around them are too gradual to require any immediate adaptations. In the deeper parts of the ocean, where sunlight cannot penetrate, life continues much as it always has. The photosynthetic revolution is initially confined to the shallow, sunlit areas of the seas, leaving vast regions of the deep ocean essentially unchanged. The deep-sea communities of anaerobic bacteria continue to process sulfur, methane, and other chemical energy sources just as they have for geological ages. The atmosphere above these slowly changing seas remains largely unaffected by the early stages of the photosynthetic revolution. The oxygen produced by the bacteria is immediately consumed by chemical reactions in the water, preventing it from escaping into the air. The atmospheric composition, rich in methane, carbon dioxide, and other gases but virtually free of oxygen, remains stable for millions of years, even as the seas below slowly transform. Weather patterns in this ancient world continue to follow the same basic principles that govern climate today, but with important differences created by the unique atmospheric composition. Without oxygen to create ozone layers, ultraviolet radiation from the sun penetrates more deeply into the atmosphere, driving photochemical reactions that create complex interactions between different atmospheric gases. These reactions create beautiful optical effects, subtle color changes in the sky as different compounds absorb and scatter sunlight in wavelength-specific ways. The temperature of this ancient world remains stable and warm, heated by the greenhouse effect of methane and carbon dioxide in the atmosphere. The gradual increase in photosynthetic activity actually helps to maintain this warmth by consuming carbon dioxide and producing organic compounds that eventually decay and release methane back into the atmosphere. The entire system maintains a delicate balance that keeps global temperatures within ranges that are favorable for life. Volcanic activity continues to play an important role in maintaining the chemical balance of the ancient world. Underwater volcanoes release fresh supplies of dissolved metals and other compounds that support both the old anaerobic communities and the new photosynthetic ones. Volcanic gases add new chemicals to the atmosphere, helping to maintain the complex chemical cycles that keep the planet's environment stable and habitable. The continents of this ancient world are still largely barren rock, sculpted by wind and water, but supporting no complex life. Occasional bacterial mats might form in coastal areas where conditions are favorable, but the land remains essentially lifeless. All the important biological activity is happening in the seas, where the warm, chemical-rich water provides ideal conditions for microbial life to flourish and evolve. As the photosynthetic bacteria continue to spread and increase their populations, they begin to form more complex and organized communities. Some species specialize in capturing different wavelengths of light, allowing multiple types of bacteria to coexist in the same area by dividing up the available solar energy. Other species develop symbiotic relationships with non-photosynthetic bacteria, creating collaborative communities where different organisms contribute different capabilities to the overall success of the group. These early microbial communities represent some of the first examples of ecosystem engineering on Earth. The photosynthetic bacteria don't just passively respond to their environment. They actively modify it in ways that make it more suitable for their own survival and growth. They create chemical gradients that other organisms can exploit. They produce organic compounds that serve as food for non-photosynthetic bacteria, and they modify the physical structure of their habitat by precipitating minerals and creating three-dimensional growth forms. The stromatolites built by these early photosynthetic communities become larger and more complex as the bacteria develop more sophisticated construction techniques. Some stromatolites grow in branching, tree-like patterns that maximize their exposure to sunlight while creating protected spaces for other organisms. Others form dome-like structures that can resist wave action and provide stable platforms for long-term bacterial growth. The rhythmic growth patterns of these ancient stromatolites create some of the most beautiful and informative geological structures on Earth. Each growth layer records the environmental conditions that existed when it was formed, preserving information about water chemistry, seasonal patterns, and bacterial activity levels. These ancient structures serve as libraries of information about Earth's early history, written in the language of bacterial growth and chemical precipitation. The diversity of photosynthetic bacteria continues to increase as evolution explores different ways of capturing and using solar energy. Some bacteria develop more efficient light harvesting systems that allow them to photosynthesize in deeper water or in areas where other bacteria have already absorbed much of the available light. Others develop protective mechanisms that allow them to survive in areas where light intensity is so high that it would damage less well-adapted organisms. The chemical signatures produced by different types of photosynthetic bacteria create distinctive fingerprints that can be detected in the water around their communities. These chemical signals serve as a form of communication, allowing bacteria to detect the presence and activity levels of other photosynthetic organisms in their vicinity. The result is the development of complex spatial patterns in bacterial distribution, with different species organizing themselves to minimize competition and maximize efficiency. As millions of years continue to pass, the cumulative effects of photosynthetic activity begin to create more noticeable changes in the ocean chemistry. The concentration of dissolved iron in the seawater gradually decreases as more and more of it is precipitated out as rust particles. The pH of the water begins to shift as the chemical balance changes in response to increased oxygen production and iron precipitation. These chemical changes create new opportunities for other types of bacteria to evolve and flourish. Some bacteria develop the ability to use the iron oxides created by photosynthetic activity as energy sources, creating the first examples of organisms that can thrive on the waste products of other organisms. Others evolve mechanisms for dealing with the changing chemical conditions, developing new enzymes and protective systems that allow them to continue functioning in a slowly oxidizing environment. The stage is being set for even more dramatic changes to come. The iron dissolved in the ancient seas represents a vast but finite reservoir that has been protecting the planet from oxygen accumulation for millions of years. As photosynthetic bacteria continue to multiply and spread, they are gradually exhausting this protective reservoir. Eventually, when most of the dissolved iron has been converted to solid particles and removed from the water, the oxygen produced by photosynthesis will have nowhere to go except into the atmosphere itself. But that dramatic transformation is still millions of years in the future. For now, the photosynthetic revolution proceeds at its own patient pace, slowly and peacefully transforming the chemistry of the ancient seas while the rest of life continues largely unchanged. The warm, metal-rich waters continue to support vast communities of anaerobic bacteria. The ancient stromatolites continue to grow and thrive, and the oxygen-free atmosphere continues to maintain the greenhouse conditions that keep the planet warm and habitable. As you float in these gradually changing waters, you can sense the enormous forces of transformation that are slowly gathering momentum beneath the surface of this apparently peaceful world. The photosynthetic bacteria around you are small and unassuming, but they are in the process of engineering one of the most profound environmental changes in Earth's history. Their patient work will eventually touch every aspect of life on the planet, challenging every organism to adapt or perish in a world that will be fundamentally different from the one their ancestors knew. Yet there is no sense of urgency or crisis in this ancient world. The changes are happening so slowly that they remain well within the adaptive capacity of life itself. Evolution has millions of years to develop responses to the slowly changing conditions. Plenty of time for new strategies and innovations to emerge. The forgotten war that is beginning is not a war of destruction, but a war of adaptation, creativity, and gradual transformation that will ultimately enrich and diversify life in ways that its participants cannot possibly imagine. As you continue your journey through these ancient waters, suspended in their warm embrace, while millions of years flow past like gentle seasons, you begin to witness the most profound and peaceful transformation in the history of life on Earth. The photosynthetic bacteria that you observe spreading through the shallow seas have continued their patient work, generation after generation, slowly but steadily increasing the amount of oxygen they release into the water. For hundreds of millions of years, this oxygen has been safely consumed by the vast reserves of dissolved iron in the ancient oceans. But now, almost imperceptibly, the balance is beginning to shift. The change begins so gradually that it would be impossible to detect without the perspective of geological time. In certain areas of the ocean where photosynthetic activity has been particularly intense, the dissolved iron concentrations have been slowly declining as more and more iron has been converted to solid rust particles and settled to the seafloor. These areas are becoming what scientists would later call iron poor, though the transition is so gentle that no individual bacterium ever experiences a sudden change in its chemical environment. As the protective reservoir of dissolved iron gradually diminishes in these pioneer regions, something unprecedented begins to happen. For the first time in Earth's history, oxygen molecules produced by photosynthetic bacteria find themselves with nowhere to go. Instead of immediately reacting with iron or other dissolved compounds, these oxygen molecules begin to accumulate in the water itself, creating the first oxygen-rich pockets in Earth's ancient seas. The initial concentrations of free oxygen are incredibly small by modern standards, perhaps only a few parts per million in the most affected areas. To put this in perspective, modern seawater contains about 8 parts per million of dissolved oxygen, and the early accumulations were perhaps 1,000 times smaller than this. Yet for organisms that have evolved over billions of years in a completely oxygen-free environment, even these tiny concentrations represent a fundamental change in their world. Oxygen, despite being essential for life as we know it today, is actually a highly reactive and potentially toxic chemical. In the reducing environment of the ancient Earth, oxygen acts like a powerful bleach or disinfectant, capable of disrupting the delicate chemical processes that keep anaerobic organisms alive. The proteins, lipids, and other organic molecules that form the basis of anaerobic life are vulnerable to oxidation. Essentially, they can be burned by oxygen even at very low concentrations. For the anaerobic bacteria that have dominated Earth's oceans for billions of years, the appearance of free oxygen in their environment represents the first existential challenge their lineages have ever faced. These organisms have evolved exquisitely efficient biochemical systems for life in an oxygen-free world, but none of their adaptations provide protection against this new chemical threat. Their cell membranes, designed to regulate the flow of familiar compounds like hydrogen sulfide and methane, are permeable to oxygen. Their enzymes, optimized for reducing chemical reactions, are damaged or destroyed by oxidizing conditions. The effects of oxygen exposure on anaerobic bacteria are not violent or dramatic, but rather like a slow, progressive weakening of their life processes. Bacteria exposed to even small amounts of oxygen find that their metabolic processes become less efficient. Their ability to reproduce slows down. Their competitive position relative to other organisms gradually deteriorates. It's not an immediate death sentence, but rather a gentle, persistent stress that makes life increasingly difficult for organisms that are not adapted to cope with oxidizing conditions. The first anaerobic communities to experience oxygen stress are those living in the shallow, sunlit areas of the ocean where photosynthetic activity is most intense. In these areas, the local production of oxygen has begun to exceed the local capacity for iron to consume it, creating small but growing zones where oxygen concentrations are rising above the background levels that these organisms can tolerate. The response of different anaerobic species to this new challenge varies considerably. Some bacteria prove to be more sensitive to oxygen than others, experiencing stress and population decline even at the lowest concentrations. These highly sensitive species begin to retreat from areas where oxygen is accumulating, seeking refuge in deeper waters or in locations where chemical conditions remain more favorable for their survival. Other anaerobic species demonstrate greater tolerance for oxidizing conditions, either through natural variation in their biochemistry or through rapid evolutionary adaptations that provide some protection against oxygen damage. These more resilient species are able to maintain their populations in mildly oxidizing environments, though often at reduced density and with decreased efficiency compared to their performance in oxygen-free conditions. The retreat of oxygen-sensitive species from the shallow waters creates ecological opportunities for organisms that can tolerate or even benefit from the changing chemical conditions. Some anaerobic bacteria evolve enhanced detoxification systems that can neutralize small amounts of oxygen before it damages their cellular machinery. Others develop protective strategies, such as producing thick biofilms or seeking shelter in microenvironments where oxygen concentrations remain low. Perhaps most significantly, some bacterial lineages begin to evolve the ability to actually use oxygen in their metabolic processes. This represents one of the most important evolutionary innovations in the history of life: the development of aerobic respiration, a process that can extract far more energy from organic compounds than any anaerobic process ever could. These early aerobic bacteria are still relatively inefficient compared to their modern descendants, but they possess a crucial advantage in an increasingly oxidizing world. The ecological relationships between different bacterial communities begin to shift as oxygen concentrations slowly increase. Areas that were once dominated by methane-producing bacteria start to show decreased methanogenic activity as these highly oxygen-sensitive organisms are forced to retreat to deeper, more protected environments. Sulfur-processing bacteria, which are somewhat more tolerant of oxidizing conditions, maintain their populations better but still experience stress in areas where oxygen levels are highest. The photosynthetic bacteria themselves, ironically, are among the organisms most affected by their own waste product. Many of the early photosynthetic lineages are actually killed by the oxygen they produce, a biological irony that demonstrates how evolution often proceeds through unintended consequences rather than purposeful design. These oxygen-sensitive photosynthetic bacteria must evolve protective mechanisms quickly or face extinction from their own metabolic byproducts. Some photosynthetic bacteria solve this problem by developing more sophisticated cellular compartmentalization, isolating their oxygen-producing photosynthetic machinery from the rest of their cellular processes. Others evolve enhanced antioxidant systems that can neutralize oxygen before it causes damage. Still, others develop behavioral adaptations, such as only photosynthesizing during certain times of day or under specific environmental conditions that minimize oxygen accumulation. The visual appearance of the ancient seas begins to change subtly as oxygen concentrations increase and bacterial communities reorganize themselves in response. Areas where oxygen levels are rising often show decreased biological activity, with fewer bacterial mats and reduced stromatolite growth as oxygen-sensitive species retreat or decline. The water in these areas becomes clearer as the reduced bacterial populations produce less organic matter and create fewer particles. In contrast, areas where anaerobic bacteria have retreated to escape oxygen exposure often show increased biological activity as populations concentrate in the remaining suitable habitat. These refugial areas can become densely packed with bacterial mats and highly active microbial communities, creating zones of intense biological activity separated by increasingly barren oxidizing regions. The chemistry of the ocean begins to show the effects of rising oxygen levels in subtle but measurable ways. As oxygen reacts with organic compounds dissolved in the water, it creates new chemical species that have never existed before in significant quantities. Some of these oxidation products are toxic to anaerobic life, adding another layer of chemical stress to environments that are already becoming challenging for oxygen-sensitive organisms. The pH of seawater begins to shift in areas where oxygen is accumulating, as oxidation reactions change the acid-base balance of the chemical environment. These pH changes can affect the solubility of minerals and the stability of organic compounds, creating additional challenges for organisms that are already struggling to adapt to the presence of oxygen itself. The temperature characteristics of the ocean also begin to change as oxygen levels rise. Oxidation reactions are generally exothermic, meaning they release heat, and the cumulative effect of countless oxidation reactions throughout the ocean begins to contribute small amounts of thermal energy to the marine environment. These temperature changes are minimal, but they add another variable to an environment that is already experiencing unprecedented chemical transformation. The seasonal patterns of oxygen production and accumulation create new temporal rhythms in the ancient seas. During periods of intense sunlight, photosynthetic activity increases, leading to higher oxygen production and greater stress on anaerobic communities. During periods of reduced light, oxygen production decreases, allowing some recovery in anaerobic populations and providing temporary relief from oxidative stress. These seasonal cycles of oxygen stress create selective pressures that favor organisms with flexible metabolic systems and stress-resistant cellular machinery. Bacteria that can temporarily shut down sensitive processes during high oxygen periods, then resume normal activity when conditions improve, gain significant advantages over species that cannot adapt their physiology to cope with variable oxidizing conditions. The deep ocean remains largely unaffected by the oxygen revolution during its early stages. The deeper waters, isolated from the surface by density differences and limited mixing, continue to maintain their ancient chemical characteristics. These deep water environments become increasingly important as refugia for anaerobic life, providing stable, oxygen-free conditions where traditional metabolic processes can continue undisturbed. However, even the deep ocean is not completely immune to the changes happening at the surface. Organic matter produced by photosynthetic bacteria eventually sinks to the deep seafloor, where its decomposition can create localized zones of chemical disturbance. Dead bacterial cells from oxygen-stressed surface communities carry with them traces of oxidized compounds that can affect deep water chemistry when they decompose. The sediments accumulating on the seafloor during this period begin to show distinctive characteristics that reflect the changing ocean chemistry. Layers deposited during times of high oxygen production contain different mineral assemblages than those deposited during oxygen-poor periods. These sedimentary records create a geological archive of the oxygen catastrophe that will eventually allow scientists to reconstruct the timing and magnitude of this ancient environmental transformation. The banded iron formations that have been accumulating for millions of years begin to show changes in their composition and structure as oxygen levels rise. The classic alternating bands of iron-rich and iron-poor sediments start to become less regular as the chemical processes controlling iron precipitation become more complex. New types of iron minerals appear in the sediments, reflecting the more oxidizing conditions of the overlying water. Volcanic activity continues to play an important role in the evolving ocean chemistry, but the gases released by underwater volcanoes now encounter a different chemical environment than they did in the purely reducing seas of earlier times. Some volcanic gases that were stable in the oxygen-free oceans are now subject to oxidation, creating new chemical compounds and reaction pathways that add to the complexity of the marine environment. The microbial communities living around volcanic vents begin to show interesting adaptations to the changing chemical conditions. Some vent organisms evolve the ability to use both reducing and oxidizing compounds for energy, giving them flexibility to cope with the variable chemistry around active volcanic sites. Others develop enhanced tolerance for the mixed chemical conditions that result from the interaction between volcanic gases and the increasingly oxidizing seawater. Atmospheric chemistry begins to show the first subtle effects of the oxygen revolution, though the atmosphere itself remains overwhelmingly oxygen-free during the early stages of this transformation. The chemical reactions happening at the ocean surface can release trace amounts of oxidized compounds into the lower atmosphere, creating new photochemical pathways that slowly begin to alter the composition of the air. These atmospheric changes are so small that they would be undetectable by any conceivable measurement technique, but they represent the first steps toward the eventual transformation of Earth's atmosphere from a reducing to an oxidizing environment. The methane-rich atmosphere of the ancient world begins to experience enhanced oxidation reactions in the lowest layers, where contact with the ocean surface exposes atmospheric gases to the oxidizing influence of the slowly rising oxygen concentrations. Weather patterns remain largely unchanged during the early stages of the oxygen catastrophe, but subtle shifts in atmospheric chemistry begin to affect the optical properties of the air. The scattering of sunlight by new atmospheric compounds creates almost imperceptible changes in the color and quality of daylight, though these changes are far too small to be noticed without sophisticated spectroscopic analysis. The biological innovation happening in response to oxygen stress represents one of the most creative periods in the history of evolution. Faced with an unprecedented chemical challenge, life responds with an explosion of new metabolic strategies, protective mechanisms, and ecological adaptations. Some of these innovations will prove to be evolutionary dead ends, but others will form the foundation for all future aerobic life on Earth. The development of oxygen tolerance and aerobic metabolism proceeds along multiple independent evolutionary pathways, with different bacterial lineages developing different solutions to the challenges posed by an oxidizing environment. Some evolve sophisticated enzyme systems that can safely handle oxygen without producing damaging byproducts. Others develop cellular compartmentalization strategies that isolate oxygen-sensitive processes from oxidizing conditions. Perhaps most importantly, some bacterial lineages begin to evolve the ability to use oxygen as the terminal electron acceptor in their respiratory processes, allowing them to extract far more energy from organic compounds than was ever possible in anaerobic environments. This innovation in aerobic respiration will eventually become the foundation for all complex, multicellular life on Earth. But during its early development, it represents just another experimental adaptation to changing chemical conditions. The Great Poisoning is proceeding slowly and peacefully, but its effects are becoming increasingly widespread as oxygen production continues to exceed the ocean's capacity to neutralize it through chemical reactions. The ancient world of purely anaerobic life is being gently but inexorably transformed into something completely different, setting the stage for even more dramatic changes that will unfold over the millions of years to come. As you float in these slowly changing waters, you can sense the magnitude of the transformation that is unfolding around you. The peaceful surface of the ancient sea conceals a biological revolution that is reshaping the fundamental chemistry of life itself. The anaerobic organisms that have dominated Earth for billions of years are being challenged to adapt or retreat, while new forms of life are evolving to exploit the opportunities created by an increasingly oxidizing world. The water around you carries the chemical signatures of this ancient struggle, traces of oxygen that represent both a deadly poison and a revolutionary opportunity, depending on the evolutionary heritage and adaptive capacity of each organism that encounters them. This is the beginning of the great transformation that will eventually create the oxygen-rich world we know today, but it is happening so slowly and gently that it seems more like a gradual awakening than a catastrophic upheaval. As you continue floating through these slowly transforming waters, watching the patient unfolding of one of Earth's most profound changes, you begin to observe something remarkable about the anaerobic organisms that have called these seas home for billions of years. rather than simply succumbing to the gradual increase in oxygen levels. These ancient life forms are demonstrating the incredible resilience and adaptability that has allowed life to persist through every challenge Earth has ever presented. They are not passive victims of environmental change, but active participants in their own survival, developing strategies and innovations that will allow many of their lineages to persist even in an increasingly oxidizing world. The response of anaerobic life to the oxygen challenge reveals the extraordinary creativity of evolution when faced with unprecedented environmental pressures. Different bacterial lineages develop different survival strategies, each one representing a unique experiment in adaptation to changing conditions. Some focus on avoidance, seeking out and colonizing environments where oxygen concentrations remain low. Others develop tolerance, evolving biochemical systems that can function despite the presence of this toxic gas. Still, others pursue a strategy of active resistance, developing mechanisms to neutralize or eliminate oxygen from their immediate environment. The bacteria that choose the path of avoidance demonstrate remarkable sophistication in their ability to sense and respond to oxygen gradients in their environment. These organisms evolve enhanced chemotactic systems, essentially chemical navigation abilities that allow them to detect even tiny concentrations of oxygen and move away from oxidizing areas toward regions where conditions remain favorable for anaerobic life. This behavior requires the development of new sensory proteins and signaling pathways that can detect oxygen with extraordinary sensitivity. Watching these bacteria navigate through the water is like observing microscopic submarines equipped with sophisticated chemical detection systems. They move through the three-dimensional environment of the ancient seas, constantly sampling the water around them for traces of oxygen and adjusting their swimming patterns to maintain their position in oxygen-free zones. Their movements create subtle patterns in the water as entire populations migrate collectively to avoid areas where oxygen concentrations are rising. The most successful oxygen-avoiding bacteria become experts at finding and colonizing environmental refugia, protected niches where anaerobic conditions persist even as the broader marine environment becomes increasingly oxidizing. These refugia include the deeper layers of the ocean, where mixing with surface waters is limited and oxygen concentrations remain low. They also include sediments and biofilms, where biological and chemical processes can quickly consume any oxygen that penetrates from the surrounding water. Some of the most fascinating refugia are found in the microenvironments created by the geological features of the seafloor. Cracks and crevices in underwater rock formations create isolated pockets of water where chemical conditions can remain stable for extended periods. Hydrothermal vents and areas of active volcanism continue to produce reducing compounds that neutralize oxygen, creating oases of anaerobic conditions in an increasingly oxidizing ocean. The bacteria that colonize these refugia often develop remarkable specializations that allow them to thrive in very specific environmental conditions. Some become extremely efficient at utilizing the limited resources available in deep water environments, developing metabolic pathways that can extract energy from chemical compounds that other organisms cannot use. Others evolve the ability to enter dormant states during periods when oxygen levels rise, then quickly resume activity when conditions improve. The strategy of developing oxygen tolerance represents a different approach to survival in the changing world. Rather than avoiding oxygen entirely, these bacteria evolve biochemical systems that can function in the presence of limited amounts of this reactive gas. This evolutionary pathway requires fundamental changes to cellular biochemistry, including the development of new enzymes and protective compounds that can prevent oxygen from damaging essential cellular components. The evolution of oxygen tolerance is a gradual process that unfolds over millions of years through countless small improvements in cellular defense mechanisms. Early steps in this evolutionary pathway include the development of simple antioxidant compounds that can neutralize small amounts of oxygen before it causes damage. These primitive antioxidant systems are relatively inefficient, but they provide enough protection to allow bacteria to survive in mildly oxidizing environments. More sophisticated oxygen tolerance mechanisms evolve as environmental pressures increase and bacterial populations have more time to adapt. Some bacteria develop specialized enzymes called catalases and peroxidases that can break down hydrogen peroxide and other toxic oxygen compounds that form when oxygen reacts with organic molecules. Others evolve enhanced DNA repair systems that can fix the damage caused by oxidative stress, allowing them to maintain genetic integrity even when exposed to harmful levels of oxygen. The development of cellular compartmentalization represents another important strategy for coping with oxygen stress. Some bacteria evolve the ability to concentrate their most oxygen-sensitive processes in specialized cellular regions that can be isolated from the external environment. This allows them to maintain essential anaerobic metabolic pathways while tolerating the presence of oxygen in other parts of their cells. Perhaps the most remarkable adaptation developed by some anaerobic bacteria is the ability to actively remove oxygen from their environment through chemical means. These organisms evolve specialized metabolic pathways that can consume oxygen as a substrate, effectively creating oxygen-free zones around their communities. This strategy allows them to maintain anaerobic conditions even in areas where oxygen is being produced by photosynthetic bacteria. The bacteria that develop oxygen-consuming capabilities often become ecosystem engineers, modifying the chemical environment around them in ways that benefit other oxygen-sensitive organisms. They create chemical gradients that other anaerobic bacteria can follow to find suitable habitat, and they establish microenvironments where traditional anaerobic metabolic processes can continue undisturbed. Some of the most successful oxygen-consuming bacteria develop the ability to use oxygen in controlled, limited ways while maintaining their fundamentally anaerobic lifestyle. These organisms evolve primitive respiratory systems that can extract energy from organic compounds using oxygen, but they do so in ways that minimize the production of toxic oxygen intermediates. This represents an early step toward the full aerobic respiration that will eventually dominate life on Earth. The social behaviors of anaerobic bacterial communities also evolve in response to oxygen stress, with many species developing enhanced cooperation and resource-sharing strategies that help their communities survive in challenging conditions. Some bacteria begin to specialize in particular aspects of community defense, with different species taking on roles such as oxygen detection, antioxidant production, or the creation of protective biofilms. Biofilm formation becomes an increasingly important survival strategy as oxygen levels rise throughout the ancient seas. These complex, multi-layered bacterial communities create their own protected microenvironments where chemical conditions can be carefully controlled and maintained. The bacteria in biofilms work together to create chemical gradients that keep oxygen concentrations low in the interior layers while allowing more tolerant species to form protective barriers on the exterior surfaces. The structure of bacterial biofilms becomes increasingly sophisticated as oxygen stress intensifies, with different bacterial species organizing themselves into specialized layers that perform different functions for the community. The outermost layers might consist of bacteria that have evolved oxygen tolerance or oxygen-consuming abilities, while the innermost layers remain dominated by traditional anaerobic species that require complete protection from oxidizing conditions. Communication between bacterial cells within these communities becomes more complex and sophisticated as the challenges of survival in an oxidizing environment increase. Bacteria evolve enhanced chemical signaling systems that allow them to coordinate their responses to oxygen stress and share information about local environmental conditions. These communication networks help bacterial communities respond more effectively to changing conditions and optimize their collective survival strategies. The metabolic flexibility of anaerobic bacteria increases dramatically as they adapt to the variable oxygen concentrations that characterize the transitional period of Earth's oxygenation. Many species evolve the ability to switch between different metabolic pathways depending on the chemical conditions in their immediate environment. When oxygen levels are low, they can use traditional anaerobic processes, but when oxygen is present, they can switch to alternative pathways that are less sensitive to oxidative stress. This metabolic flexibility requires the evolution of sophisticated regulatory systems that can sense environmental conditions and adjust cellular biochemistry accordingly. Bacteria develop new genetic switches and control mechanisms that allow them to rapidly reconfigure their metabolic machinery in response to changing chemical conditions. These regulatory innovations represent some of the most sophisticated biological control systems that have ever evolved. The reproductive strategies of anaerobic bacteria also adapt to the challenges of life in an increasingly oxidizing world. Some species evolve enhanced DNA protection and repair mechanisms that ensure genetic integrity during reproduction, even when oxygen levels are elevated. Others develop reproductive timing strategies that synchronize reproduction with periods when oxygen concentrations are lowest, minimizing the risk of genetic damage during the vulnerable process of cell division. Horizontal gene transfer, the sharing of genetic material between different bacterial species, becomes an increasingly important mechanism for spreading beneficial adaptations throughout anaerobic communities. Bacteria that evolve successful oxygen tolerance mechanisms can share these innovations with other species, allowing beneficial adaptations to spread rapidly through bacterial populations without waiting for the slower process of vertical inheritance through reproduction. The geographical distribution of anaerobic bacteria begins to change dramatically as oxygen levels rise in different parts of the ancient oceans. Species that were once widely distributed throughout the marine environment become increasingly restricted to specific regions where conditions remain favorable for anaerobic life. This geographical fragmentation creates opportunities for isolated populations to evolve specialized adaptations to their particular local conditions. Some bacterial lineages develop remarkable mobility strategies that allow them to track favorable conditions as they shift geographically over time. These bacteria evolve enhanced swimming abilities and sophisticated navigation systems that allow them to migrate over large distances in search of suitable habitat. Their movements create dynamic population patterns that respond to the changing chemistry of the ancient seas. The deep ocean becomes increasingly important as a refuge for anaerobic life as surface waters become more oxidizing. The bacteria that colonize these deep water environments often evolve specialized adaptations for life under high pressure and in nutrient-poor conditions. They develop highly efficient metabolic systems that can extract energy from the limited resources available in the deep sea, and they evolve stress-resistant cellular structures that can withstand the extreme conditions of the abyssal environment. Symbiotic relationships between different bacterial species become more common and more sophisticated as environmental pressures increase and resources become more limited. Some bacteria develop intimate partnerships where one species provides protection from oxygen stress, while the other contributes essential nutrients or metabolic capabilities. These symbiotic associations often evolve into highly integrated systems, where the partner species become dependent on each other for survival. The timing of bacterial activities becomes more precisely synchronized with environmental cycles as oxygen concentrations fluctuate in response to photosynthetic activity and other environmental factors. Many bacterial species evolve biological clocks that allow them to coordinate their metabolic activities with daily and seasonal patterns of oxygen production, minimizing their exposure to oxidative stress while maximizing their access to resources. Temperature regulation becomes an important factor in bacterial survival strategies, as oxygen toxicity is often temperature-dependent. Some bacteria evolve the ability to modify their local temperature environment through metabolic activity, creating thermal refugia where oxygen toxicity is reduced. Others develop behavioral strategies that allow them to seek out temperature zones where their oxygen tolerance mechanisms are most effective. The chemical complexity of bacterial waste products increases as species develop new metabolic pathways for dealing with oxygen stress. Some bacteria begin producing specialized compounds that can neutralize oxygen or provide protection for other community members. These chemical innovations create new ecological interactions and dependencies that increase the overall resilience of anaerobic communities. Competition between different bacterial species for access to oxygen-free environments intensifies as suitable habitat becomes more limited. However, this competition often drives the evolution of more efficient resource utilization and more sophisticated ecological strategies rather than simple aggressive interactions. Bacterial communities develop complex hierarchies and resource-sharing arrangements that allow multiple species to coexist in limited refugial habitats. The seasonal patterns of bacterial activity become more pronounced as environmental conditions become more variable and challenging. During periods when oxygen production is high, many bacterial communities reduce their activity levels and focus on survival and maintenance. During periods when oxygen levels are lower, they increase their metabolic activity and focus on growth and reproduction. The evolution of stress response systems becomes a major focus of bacterial adaptation during this period. Bacteria develop increasingly sophisticated mechanisms for detecting environmental stress and adjusting their physiology accordingly. These stress response systems often involve complex genetic regulatory networks that can coordinate the expression of hundreds of genes in response to changing environmental conditions. As you observe these remarkable adaptations unfolding over millions of years, you begin to appreciate the incredible ingenuity and resilience of life when faced with existential challenges. The anaerobic bacteria are not simply passive victims of environmental change, but active participants in shaping their own evolutionary destiny. Their strategies for survival in an increasingly oxidizing world demonstrate the fundamental creativity and adaptability that characterizes all living systems. The ancient seas around you continue to support vast communities of anaerobic bacteria, even as oxygen levels slowly rise and conditions become more challenging. These organisms represent the continuation of biological traditions that stretch back to the very beginning of life on Earth, and their persistence in the face of unprecedented environmental change demonstrates the remarkable resilience of the living world. The warm, chemical-rich waters continue to provide the basic requirements for anaerobic life, even as they slowly transform into something completely different. The bacteria floating around you are simultaneously ancient and innovative, carrying forward billions of years of evolutionary heritage while developing new strategies for survival in a changing world. Their quiet struggle represents one of the most important chapters in the history of life on Earth, and their success in adapting to oxygen stress will help ensure that the biological innovations of the anaerobic world will persist even as the planet transforms into an oxygen-rich environment. As you continue your gentle journey through these transforming waters, suspended in the warm embrace of an ocean that has witnessed billions of years of life's patient evolution, you begin to notice something extraordinary happening to the very appearance of the ancient seas around you. The changes are subtle at first, like the gradual shift of light at sunset, but as millions of years continue to pass in their stately procession, the visual transformation of the marine environment becomes one of the most striking aspects of the Great Oxygenation Event. The crystal-clear waters that once characterized these primordial seas are slowly taking on new colors and textures as the chemical reactions driven by oxygen production create substances that have never existed in significant quantities before in Earth's oceans. The most dramatic of these changes involves the formation of iron oxides, essentially rust particles, as the oxygen produced by photosynthetic bacteria encounters the vast reserves of dissolved iron that have been accumulating in the seas for hundreds of millions of years. The process begins almost imperceptibly, with individual oxygen molecules finding their way to dissolved iron atoms and forming the first molecular bonds that will eventually create solid particles of iron oxide. Each reaction is microscopic, involving just a few atoms, but the cumulative effect of trillions upon trillions of these reactions creates visible changes in the water that gradually transform the appearance of entire ocean basins. The first iron oxide particles to form are incredibly small, smaller than the wavelength of visible light, and they create a subtle haziness in the water that's barely perceptible at first. As more and more iron reacts with oxygen, these particles grow larger and more numerous, beginning to scatter light in ways that create the first hints of color change in the ancient seas. The water takes on a faint reddish tinge in areas where oxygen production is highest, like watercolor paint being slowly mixed into clear water. As the process continues over millions of years, the color changes become more pronounced and widespread. Areas of the ocean that were once perfectly transparent now show distinct coloration, ranging from pale amber to deep rust red, depending on the concentration of iron oxide particles in the water. The effect is not uniform. Different regions of the ocean show different intensities of coloration based on local rates of oxygen production and iron availability. The most intense coloration appears in shallow, coastal areas where photosynthetic bacterial communities are most active. These regions become almost like underwater rust clouds, with visibility reduced by the dense concentrations of iron oxide particles suspended in the water. The particles create beautiful optical effects as they scatter and absorb sunlight, producing subtle color gradations that shift and change as currents move the particle-laden water through different light conditions. In deeper waters, where oxygen concentrations are lower and iron precipitation is less intense, the color changes are more subtle but still noticeable. These areas maintain better water clarity while showing gentle tints of yellow and orange that speak of the chemical transformation happening throughout the marine environment. The contrast between the rust-colored shallows and the clearer deep waters creates a layered, stratified appearance that gives the ancient oceans a completely new visual character. The seasonal patterns of oxygen production create temporal variations in the intensity of iron precipitation and water coloration. During periods when photosynthetic activity is highest, the rate of iron oxide formation increases, leading to more intense coloration and reduced water clarity. During periods of lower photosynthetic activity, particle formation slows, allowing some of the suspended iron oxides to settle out of the water column and partially restoring clarity. These seasonal cycles create dynamic visual patterns in the ancient seas, with the intensity of rust coloration waxing and waning in rhythm with the biological cycles of the photosynthetic bacteria. The effect is like watching a slow-motion aurora in the water, with waves of color intensity moving through the marine environment in response to changing biological activity levels. The iron oxide particles themselves are remarkable structures when viewed at the microscopic level. Each particle represents a complex mineral formation with its own unique crystalline structure and chemical composition. Some particles form as simple, spherical aggregates of iron and oxygen atoms, while others develop more complex structures with multiple layers and intricate internal geometries. The formation of these particles is not a random process, but rather follows specific chemical and physical laws that govern crystal growth and mineral precipitation. Different environmental conditions, temperature, pH, the presence of other dissolved substances, influence the type and structure of iron oxides that form, creating a diverse array of particle types with different optical properties and settling behaviors. Some iron oxide particles are relatively dense and settle quickly to the seafloor, where they accumulate in layers that will eventually become part of the geological record. Others are lighter and more buoyant, remaining suspended in the water column for extended periods and creating the persistent coloration that characterizes the rust-colored seas. Still others form complex aggregates that can trap other particles in organic matter, creating composite structures that settle at intermediate rates. The settling of iron oxide particles creates one of the most important geological processes in Earth's history. As these particles accumulate on the seafloor, they form distinctive sedimentary layers that record the timing and intensity of oxygen production events. These layers alternate with other types of sediment deposited during periods when iron precipitation was less active, creating the banded iron formations that represent some of the most beautiful and informative rock sequences on Earth. The banded iron formations that accumulate during this period are like frozen music, with alternating bands of iron-rich and iron-poor sediment, creating rhythmic patterns that reflect the complex interplay between biological oxygen production and chemical iron precipitation. Each band represents a specific interval of time when particular environmental conditions prevailed, and the overall pattern records the gradual increase in oxygen production over millions of years. The colors preserved in these ancient sediments are remarkable in their variety and intensity. Iron-rich layers often show deep reds, oranges, and browns, reflecting the various types of iron oxides that precipitated under different chemical conditions. Iron-poor layers tend to be gray, black, or greenish, composed of other minerals that accumulated when iron precipitation was less active. The contrast between these different colored layers creates some of the most visually striking rock formations on Earth. The formation of banded iron formations requires very specific environmental conditions that existed only during the transition period, when oxygen was beginning to accumulate in significant quantities but had not yet reached modern levels. This makes these geological formations unique records of one of the most important transitions in Earth's history, preserving detailed information about the pace and character of the Great Oxygenation Event. The chemical processes that create iron oxides also affect other dissolved metals in the ancient seas, leading to the precipitation of a variety of different mineral phases. Manganese, copper, zinc, and other metals react with oxygen to form their own oxide and hydroxide compounds, adding additional colors and textures to the transforming marine environment. These secondary precipitation reactions create a complex chemical cascade that affects the entire dissolved metal inventory of the ancient oceans. The removal of dissolved iron from seawater through oxide precipitation has profound effects on marine chemistry beyond just the visual changes. Iron is an essential nutrient for many types of bacteria, and its removal from solution can limit biological productivity in some areas while enhancing it in others where iron oxide particles provide alternative sources of this crucial element. Some bacterial communities adapt to the changing iron availability by developing enhanced iron uptake systems that can extract this essential nutrient from iron oxide particles rather than relying on dissolved iron. These adaptations require the evolution of new enzymes and cellular machinery capable of reducing solid iron oxides back to soluble forms that can be used for biological processes. The optical properties of the rust-colored seas create new environmental conditions that affect photosynthetic bacteria and other light-dependent organisms. The increased light scattering caused by suspended iron oxide particles reduces the depth to which sunlight can penetrate, creating deeper, more extensive twilight zones in the water column. This affects the distribution and productivity of photosynthetic communities, which must adapt to reduced light availability or migrate to shallower waters. Some photosynthetic bacteria respond to the reduced light penetration by developing more efficient light harvesting systems that can capture and utilize the filtered light that penetrates through the particle-laden water. Others evolve the ability to use different wavelengths of light that are less affected by scattering from iron oxide particles, allowing them to maintain photosynthetic activity even in highly colored water. The changes in water optical properties also affect the behavior of other organisms that rely on vision or light-dependent navigation. The reduced water clarity and altered light environment require adaptations in sensory systems and behavioral strategies. Some organisms develop enhanced chemotactic abilities to compensate for reduced visual information, while others evolve modified visual systems that can function effectively in the altered light environment. Temperature dynamics in the rust-colored seas become more complex as suspended particles affect heat absorption and distribution. Iron oxide particles are efficient absorbers of solar radiation, and their presence in the water column creates localized heating effects that can influence water circulation patterns. Areas with high concentrations of suspended particles tend to warm more rapidly during daylight hours, creating thermal gradients that drive convective mixing and affect the distribution of dissolved substances. The thermal effects of particle absorption also influence seasonal patterns of water column stability and mixing. During periods of intense solar heating, particle-rich surface waters can become significantly warmer than the underlying clear water, creating strong thermal stratification that limits vertical mixing. During cooler periods, The enhanced heat loss from particle-rich surface waters can drive more vigorous convective circulation. These thermal effects create new microenvironments within the ancient seas, with different temperature regimes existing at different depths and in different regions, depending on local particle concentrations. The thermal heterogeneity provides opportunities for specialized bacterial communities to evolve adaptations to specific temperature niches within the water column. The acoustic properties of the rust-colored seas also change as suspended particles affect the propagation of sound waves through the water. The scattering and absorption of acoustic energy by iron oxide particles creates new sound transmission characteristics that affect any organisms that rely on acoustic communication or echolocation. These changes require adaptations in communication strategies and sensory systems for organisms that depend on sound-based information. Current patterns and water circulation in the ancient oceans begin to respond to the physical properties of particle-laden water. Iron oxide particles add mass to the water column, creating density gradients that can influence the movement of water masses. Areas with high particle concentrations become slightly denser than clear water, affecting buoyancy and circulation patterns on both local and regional scales. The settling of iron oxide particles creates vertical fluxes of material that can influence ocean circulation through their effects on water density. As particles settle through the water column, they carry with them small amounts of water that can contribute to downward flow patterns. The cumulative effect of countless settling particles can influence large-scale circulation patterns over geological time periods. Chemical gradients become more pronounced in the rust-colored seas as iron precipitation creates zones of depletion and enrichment for various dissolved substances. Areas where active iron precipitation is occurring show reduced concentrations of dissolved iron and elevated oxygen levels, while areas where particle settling is intense may show different chemical signatures related to the decomposition of organic matter associated with the settling particles. The chemical heterogeneity created by iron precipitation processes provides new opportunities for bacterial communities to specialize in different chemical environments within the same water body. Some bacteria evolve to thrive in iron-depleted, oxygen-rich environments, while others specialize in iron-rich zones where particle dissolution provides access to this essential nutrient. Biological productivity patterns shift in response to the changing chemical and physical environment of the rust-colored seas. Some areas experience enhanced productivity as iron oxide particles provide new sources of nutrients through dissolution and weathering processes. Other areas may show reduced productivity due to decreased light penetration or altered chemical conditions that are less favorable for particular types of organisms. The visual beauty of the rust-colored seas represents one of the most striking examples of biological activity reshaping the physical appearance of the Earth's surface. The colors created by iron oxide precipitation are not random or chaotic, but rather reflect the organized patterns of biological activity and chemical processes that govern the formation and distribution of these particles. The patterns of coloration in the ancient seas create natural artwork on a planetary scale, with swirls and gradients of color that reflect the complex interactions between biological, chemical, and physical processes. These patterns change constantly as currents redistribute particles, biological activity waxes and wanes, and chemical gradients shift in response to changing environmental conditions. As you float in these transformed waters, surrounded by the gentle rust-colored haze that speaks of one of the most important chemical transformations in Earth's history, you can appreciate the incredible beauty that emerges when life reshapes its environment on a planetary scale. The iron oxides suspended around you represent both the waste products of photosynthetic bacteria and the raw materials for future geological formations that will preserve the record of this ancient transformation for billions of years. The warm, colored waters continue to support diverse communities of bacteria and other microorganisms, demonstrating that environmental change, even on a planetary scale, doesn't necessarily mean the destruction of life, but rather its transformation and adaptation to new conditions. The rust-colored seas represent a transitional phase in Earth's history, when the planet was learning to accommodate both the ancient anaerobic traditions and the revolutionary new possibilities created by oxygen production. The gentle circulation of these particle-laden waters creates ever-changing patterns of light and color that transform the underwater landscape into something that seems almost magical in its beauty. The iron oxides catch and scatter sunlight in ways that create underwater auroras of rust and gold, amber and orange, painting the ancient seas with colors that speak of transformation, adaptation, and the incredible creativity of life working in partnership with chemistry and physics to reshape an entire world. As you continue your peaceful journey through these transforming waters, witnessing the gradual but inexorable changes that are reshaping the ancient world, you begin to observe one of the most poignant and remarkable chapters in the story of life's adaptability. The anaerobic organisms that have dominated Earth's oceans for billions of years are beginning a great migration, not across geographical distances, but into the hidden spaces and forgotten corners of their aquatic world. This is not a panicked flight or desperate escape, but rather a patient, methodical retreat into environments where the old ways of life can continue undisturbed by the chemical revolution happening in the sunlit waters above. The migration begins subtly, with individual bacteria and small communities gradually shifting their distribution patterns in response to the slowly rising oxygen concentrations in their traditional habitats. These movements are so gradual that they unfold over thousands of generations, allowing plenty of time for populations to adapt to new environmental conditions as they encounter them. There is no sudden exodus or mass abandonment of habitat, but rather a gentle, persistent drift toward environments that remain hospitable to anaerobic life. The first and most obvious refuges for oxygen-sensitive organisms are found in the deeper layers of the ancient seas, where the influence of surface oxygen production is minimized by the limited mixing between surface and deep waters. These deep water environments maintain their ancient chemical characteristics: low oxygen, high concentrations of reduced compounds, and stable temperature conditions that have supported anaerobic life for geological ages. The journey to these deep water refuges is like descending into an underwater sanctuary where time moves more slowly and change comes more gently. As you follow the migrating bacteria into the depths, you notice how the water gradually becomes clearer and more transparent, free from the rust-colored iron oxide particles that characterize the oxidizing surface waters. The temperature becomes more stable, the pressure increases gradually, and the chemical environment takes on the familiar characteristics of the ancient, oxygen-free seas. In these deep waters, anaerobic bacterial communities can maintain their traditional ways of life almost unchanged by the revolution happening above. The same metabolic pathways that have sustained these organisms for billions of years continue to function efficiently in the stable chemical environment of the deep ocean. Sulfur-reducing bacteria continue to process hydrogen sulfide and elemental sulfur. Methane-producing bacteria continue to generate their gaseous waste products. An entire complex web of anaerobic interactions continues to function much as it always has. The deep-sea refuges become centers of evolutionary conservation, where ancient lineages can persist and maintain their genetic heritage even as surface environments become increasingly hostile to their survival. These communities serve as living museums of Archean biochemistry, preserving metabolic processes and ecological relationships that represent billions of years of evolutionary refinement. But the deep ocean is not the only refuge available to oxygen-sensitive organisms. Some of the most creative and sophisticated retreats are found in the microscopic spaces within sediments, where bacterial communities can create and maintain their own chemical environments regardless of conditions in the overlying water. These sedimentary refuges represent some of the most ingenious solutions to the challenge of surviving in an oxidizing world. The migration into sedimentary environments requires remarkable adaptations for life in spaces that are measured in micrometers rather than meters. Bacteria that colonize these environments must evolve the ability to navigate through the intricate three-dimensional maze of sediment particles, finding pathways through spaces that are barely larger than their own cell bodies. They must also develop enhanced efficiency in their metabolic processes, since the limited space and restricted flow of nutrients make resource acquisition much more challenging than in open water environments. Within the sediment matrix, bacteria create sophisticated chemical microenvironments that can maintain anaerobic conditions even when the overlying water contains significant concentrations of oxygen. They accomplish this through collective metabolic activity that rapidly consumes any oxygen that penetrates into their domain, creating oxygen-free zones that can extend several centimeters into the sediment column. The bacterial communities in sedimentary refuges develop remarkable cooperation and coordination, with different species working together to maintain the chemical conditions that all of them require for survival. Some species specialize in consuming oxygen and creating the anaerobic environment, while others focus on processing organic matter and generating the chemical energy sources that support the entire community. Still others concentrate on producing protective compounds or maintaining the physical structure of the bacterial habitat. These sedimentary communities create some of the most complex and sophisticated ecosystems on Earth, with intricate food webs and chemical cycles that operate entirely within spaces that are invisible to the naked eye. The bacteria in these communities communicate through chemical signals, coordinate their metabolic activities, and even engage in what appears to be primitive forms of agriculture, cultivating specific types of organic matter that serve as food sources for the community. Another important type of refuge is found in association with geological features that continue to produce reducing compounds even as the broader ocean environment becomes oxidizing. Hydrothermal vents, underwater volcanic systems, and areas of active seafloor spreading continue to release hydrogen sulfide, methane, and other reduced compounds that neutralize oxygen and maintain locally anaerobic conditions. These geological refuges become oases of ancient chemistry in an increasingly modern world, supporting thriving communities of bacteria that follow traditional metabolic pathways while surrounded by environments that would otherwise be hostile to their survival. The bacteria that colonize these refuges often develop enhanced tolerance for the extreme conditions: high temperatures, unusual chemical compositions, variable flow rates that characterize geologically active environments. The communities around hydrothermal vents become particularly sophisticated, with bacterial populations that can exploit the chemical energy released by volcanic processes while maintaining the anaerobic conditions necessary for their survival. These communities develop complex spatial organization, with different bacterial species positioned at different distances from the vents to take advantage of optimal chemical and temperature conditions for their particular metabolic requirements. Some of the most remarkable refuges are created by the biological activities of other organisms, particularly the formation of biofilms and microbial mats that can maintain their own internal chemical environments. These biological structures become like underwater cities, with complex architecture and sophisticated infrastructure that supports diverse communities of anaerobic bacteria. The biofilms that serve as refuges for anaerobic bacteria are marvels of biological engineering, with multiple layers of different bacterial species that each contribute to the overall function and stability of the structure. The outer layers often consist of bacteria that can tolerate or even consume oxygen, creating a protective barrier that shields the interior from oxidizing conditions. The inner layers maintain traditional anaerobic conditions and support the bacterial species that require complete protection from oxygen. The construction and maintenance of these biofilm refuges requires remarkable coordination between different bacterial species, with some organisms specializing in producing the structural materials that hold the biofilm together, others focusing on creating the chemical gradients that maintain optimal conditions, and still others serving as the primary producers or processors of organic matter that feeds the entire community. Communication within biofilm communities becomes increasingly sophisticated as these structures grow larger and more complex. Bacteria develop enhanced chemical signaling systems that allow them to coordinate their activities across the entire biofilm structure, ensuring that chemical gradients are maintained, structural integrity is preserved, and resources are distributed efficiently throughout the community. The temporal patterns of activity within biofilm refuges often become synchronized with external environmental cycles, allowing these communities to optimize their survival strategies in response to changing conditions in the surrounding water. During periods when oxygen concentrations in the external environment are highest, biofilm communities may reduce their overall activity levels and focus on maintaining their protective barriers. During periods when oxygen levels are lower, they may increase their metabolic activity and engage in growth and reproduction. Some biofilm communities develop the ability to temporarily seal themselves off from the external environment during periods of extreme oxygen stress, creating essentially closed systems that can maintain their internal chemistry independently of external conditions. These sealed biofilms can survive extended periods of exposure to oxidizing conditions, then resume normal activity when external conditions become more favorable. The geographical distribution of refuges creates new patterns of habitat connectivity and isolation that influence the evolution and ecology of anaerobic bacterial communities. Some refuges are connected by pathways of suitable habitat that allow bacterial populations to migrate between them and maintain genetic exchange. Others become isolated islands of anaerobic life, surrounded by hostile oxidizing environments, leading to the evolution of specialized endemic populations. The deep-sea refuges, in particular, become connected by a network of deep water currents that allow bacterial populations to spread between suitable habitats while avoiding the oxidizing surface waters. These deep water migration routes become highways for anaerobic life, maintaining genetic diversity and allowing successful adaptations to spread throughout the deep-sea bacterial community. The seasonal patterns of refuge occupation often develop in response to temporal variations in oxygen production and environmental conditions. Some bacterial populations learn to migrate between different types of refuges depending on seasonal conditions, spending periods of high oxygen stress in deep water or sedimentary refuges, then returning to more productive near-surface environments when conditions improve. These seasonal migration patterns require sophisticated environmental sensing abilities and behavioral coordination that allow bacterial populations to anticipate changing conditions and respond appropriately. Some communities develop biological clocks that help them time their migrations to coincide with optimal environmental conditions, while others evolve enhanced chemical sensing systems that allow them to track environmental changes in real time. The refuges themselves often undergo seasonal changes in their capacity to support anaerobic life. Sedimentary refuges may become more or less suitable depending on seasonal variations in organic matter input and oxygen penetration. Hydrothermal vent communities may experience seasonal changes in the chemical composition and flow rates of vent fluids. Biofilm refuges may grow and shrink in response to seasonal variations in nutrient availability and environmental stress. The adaptation of anaerobic bacteria to life in refuges drives the evolution of numerous specialized characteristics that distinguish refuge populations from their ancestral forms. Some bacteria develop enhanced motility that allows them to navigate efficiently through confined spaces or complex three-dimensional habitats. Others evolve increased metabolic efficiency that allows them to survive in nutrient-poor environments or compete successfully for limited resources. Stress tolerance becomes a particularly important adaptation for refuge-dwelling bacteria, as these environments often present challenges beyond just oxygen toxicity. Deep-sea refuges subject bacteria to high pressure and low temperatures. Sedimentary refuges create space limitations and resource constraints. Geological refuges expose bacteria to extreme temperatures and unusual chemical compositions. Each type of refuge selects for different combinations of stress tolerance traits. The symbiotic relationships between different bacterial species become more important and more sophisticated in refuge environments. where cooperation can mean the difference between survival and extinction. Some refuge communities develop highly integrated partnerships where different species become completely dependent on each other for essential life functions. These partnerships often involve complex biochemical exchanges and coordinated life cycles that allow the partner species to function as unified systems. The genetic diversity within refuge populations often increases as these communities accumulate adaptive mutations and beneficial gene transfers that enhance their survival in challenging environments. However, some refuges may also experience genetic bottlenecks if population sizes become very small or if isolated populations lose genetic diversity through random drift. The refuges that emerge during the Great Oxygenation Event will persist for billions of years, maintaining communities of anaerobic bacteria that continue to follow ancient metabolic pathways even in the modern oxygen-rich world. Many of these refuge environments still exist today, supporting thriving communities of bacteria that are direct descendants of the organisms that first retreated to the shadows during the oxygen catastrophe. The study of modern anaerobic refuge communities provides important insights into the strategies and adaptations that allowed life to survive the Great Oxygenation Event. These communities serve as windows into the ancient world, preserving ecological relationships and metabolic processes that have remained essentially unchanged for billions of years. As you explore these various refuges, drifting through the deep waters, penetrating into the microscopic spaces within sediments, and observing the complex architecture of biofilm communities, you begin to appreciate the incredible ingenuity and resilience that life demonstrates when faced with existential challenges. The retreat to the shadows is not a defeat or a failure, but rather a strategic adaptation that allows ancient forms of life to persist and thrive even as the world around them transforms beyond recognition. The warm, stable waters of these refuges continue to support the ancient traditions of anaerobic life, maintaining the chemical cycles and ecological relationships that have sustained these communities for geological ages. In these protected environments, the forgotten war between oxygen and anaerobic life reaches a kind of peaceful resolution, with each side finding ways to coexist in a world that has room for both ancient and modern forms of life. The bacteria that populate these refuges are not relics or evolutionary failures, but rather successful specialists that have found ways to thrive in environments that remain largely unchanged from the ancient world. Their persistence demonstrates that environmental change, even on a planetary scale, doesn't necessarily mean the elimination of older forms of life, but rather their redistribution into environments where they can continue to flourish. As you rest in these peaceful refuges, surrounded by the gentle activities of bacteria that maintain traditions stretching back to the very beginning of complex life on Earth, you can appreciate the remarkable continuity that exists between the ancient and modern worlds. The retreat to the shadows represents not an ending, but a transformation that allows the past to persist within the present, creating a richer and more diverse biosphere that benefits from both ancient wisdom and modern innovation. As you drift upward from the peaceful refuges where anaerobic life has found sanctuary, returning to the transforming waters of the ancient seas, you begin to witness the emergence of something entirely new in the history of life on Earth. While the oxygen-sensitive organisms have been adapting through retreat and protection strategies, other lineages have been pursuing a radically different approach to the challenge of an oxidizing world. These pioneering organisms are not merely tolerating oxygen or avoiding it. They're learning to embrace it, to harness its chemical power, and to use it as the foundation for entirely new ways of being alive. The evolution of aerobic life represents one of the most remarkable transformations in the history of biology, comparable to the original emergence of life itself. The bacteria that begin this evolutionary journey start from the same anaerobic heritage as their refuge-seeking relatives, but they embark on a path that will fundamentally reshape what it means to be a living organism. This transformation unfolds slowly and gently over millions of years, with each generation building upon the innovations of the previous one, an impatient process of biological discovery. The first steps toward aerobic life are tentative and experimental, involving bacterial lineages that develop the ability to tolerate small amounts of oxygen without being damaged by its reactive chemistry. These early pioneers are not yet true aerobic organisms. They still rely primarily on anaerobic metabolic pathways for their energy needs, but they possess enhanced resistance to oxygen toxicity that allows them to survive in environments that would be lethal to their more sensitive relatives. The protective mechanisms that these early oxygen-tolerant bacteria develop are marvels of biochemical engineering. They evolve sophisticated antioxidant systems that can neutralize the harmful byproducts of oxygen chemistry before they damage essential cellular components. They develop enhanced DNA repair mechanisms that can fix the oxidative damage that inevitably occurs when living in an oxygen-containing environment. They create specialized cellular compartments that can isolate oxygen-sensitive processes from the oxidizing external environment. As these protective systems become more efficient and sophisticated, some bacterial lineages begin to experiment with using oxygen in limited ways for their metabolic processes. This represents a fundamental shift in biological strategy. Instead of treating oxygen as a toxic waste product to be avoided or neutralized, these innovative bacteria begin to explore its potential as a useful chemical resource. The early experiments with oxygen utilization are remarkably conservative and carefully controlled. The bacteria that attempt these innovations must balance the potential energy benefits of oxygen chemistry against the substantial risks of oxidative damage to their cellular machinery. They develop metabolic pathways that can extract energy from organic compounds using oxygen, but they do so in ways that minimize the production of harmful byproducts and maintain strict control over the chemical reactions involved. The energy yields from these early aerobic processes are initially quite modest, offering only small advantages over traditional anaerobic metabolism. However, even small energetic advantages can provide significant competitive benefits over evolutionary timescales, especially in environments where resources are limited or where other forms of energy are becoming scarce due to competition from other organisms. As millions of years pass and these early aerobic systems become more refined, the energy advantages of oxygen-based metabolism become increasingly apparent. Aerobic respiration can extract far more energy from organic compounds than any anaerobic process, providing aerobic organisms with access to energy resources that their anaerobic competitors cannot fully exploit. This energetic advantage begins to translate into competitive advantages in growth rate, reproduction, and environmental tolerance. The bacteria that master aerobic metabolism begin to show remarkable improvements in their overall biological performance. They can grow faster, reproduce more frequently, and maintain larger population sizes than their anaerobic relatives. They can also colonize environments that were previously unsuitable for bacterial life, such as highly oxidizing surface waters where anaerobic bacteria cannot survive. The success of early aerobic bacteria creates positive feedback loops that accelerate the development of aerobic capabilities throughout the bacterial community. As aerobic organisms become more abundant and successful, they create environmental conditions that favor the evolution of aerobic traits in other lineages. The oxygen they consume in their metabolic processes creates oxygen gradients that other bacteria can exploit, while their waste products provide new resources that can support additional aerobic innovations. The diversification of aerobic bacteria proceeds rapidly once the basic principles of oxygen metabolism are established. Different lineages develop specialized approaches to aerobic life, exploiting different aspects of oxygen chemistry and colonizing different environmental niches within the increasingly oxidizing world. Some bacteria specialize in high oxygen environments where they can take full advantage of aerobic metabolism, while others develop the ability to function efficiently across a wide range of oxygen concentrations. The metabolic innovations developed by aerobic bacteria extend far beyond simple oxygen respiration. These organisms evolve complex biochemical pathways that can process a wide variety of organic and inorganic compounds using oxygen as an oxidizing agent. They develop the ability to break down complex organic molecules that anaerobic bacteria cannot fully utilize, accessing energy sources that were previously unavailable to life. Some aerobic bacteria evolve the ability to use oxygen for biosynthetic processes, as well as energy generation, incorporating oxygen atoms into the structure of organic molecules in ways that create new types of biological compounds. These oxygen-containing organic molecules often have properties that are superior to their oxygen-free analogs. They may be more stable, more reactive, or more efficient at performing specific biological functions. The cellular architecture of aerobic bacteria becomes increasingly sophisticated as these organisms adapt to life in an oxidizing environment. They develop specialized organelles and cellular compartments that can safely contain and control oxygen chemistry. They evolve enhanced membrane systems that can regulate the flow of oxygen and other reactive compounds into and out of different parts of the cell. The sensory capabilities of aerobic bacteria also evolve to take advantage of the new chemical environment created by oxygen abundance. They develop sophisticated chemotactic systems that can detect oxygen gradients and guide the bacteria toward optimal oxygen concentrations for their metabolic needs. They evolve the ability to sense and respond to the oxidation state of their environment, allowing them to adjust their metabolism and behavior in response to changing chemical conditions. As you continue floating through these transformed waters, now millions of years deeper into the Great Oxygenation Event, you begin to appreciate the magnitude of the planetary transformation that has unfolded around you. What began as a subtle chemical change in localized areas of the ancient seas has now become a global phenomenon that is reshaping every aspect of Earth's environment. The world you observe now bears little resemblance to the oxygen-free paradise where this journey began, yet it possesses its own unique beauty and complexity that speaks to life's remarkable ability to adapt and innovate in response to changing conditions. The atmosphere above these ancient seas has undergone perhaps the most dramatic transformation of all. The oxygen-free air of the early Earth has gradually given way to an atmosphere that contains measurable concentrations of this reactive gas. The change has been so gradual that no individual organism has ever experienced it as a sudden shift, but the cumulative effect represents one of the most profound environmental changes in the planet's history. The oxygen in the atmosphere creates new chemical processes that transform the very nature of weather and climate on Earth. The formation of ozone layers in the upper atmosphere begins to provide protection from harmful ultraviolet radiation, creating new opportunities for life to colonize environments that were previously too dangerous for biological activity. The enhanced chemical reactivity of the oxidizing atmosphere drives new types of weathering processes that alter the composition of rocks and minerals on the planet's surface. The visual appearance of the world has been transformed by the chemical changes accompanying oxygenation. The rust-colored seas that characterize the height of iron precipitation have gradually cleared as the planet's iron inventory has been largely converted to solid oxides and removed from the water column. The ancient oceans now show colors and optical properties that are much closer to those of modern seas, with clear blue-green waters that allow sunlight to penetrate to greater depths than was possible during the rust-colored phase. The clearing of the ocean waters creates new opportunities for photosynthetic organisms to colonize deeper environments and expand their ecological range. The enhanced light penetration supports larger and more diverse communities of photosynthetic bacteria, which in turn accelerate the production of oxygen and further drive the transformation of the marine environment. The seafloor itself has been transformed by the millions of years of iron precipitation and aerobic bacterial activity. Vast deposits of banded iron formations now cover large areas of the ocean bottom, creating new geological features that alter patterns of water circulation and sediment deposition. These iron-rich deposits become important resources for iron-utilizing bacteria and create new types of chemical microenvironments that support specialized bacterial communities. The chemical cycles that govern life in the ancient seas have been completely reorganized by the rise of aerobic metabolism and the transformation of ocean chemistry. The simple reducing chemistry that dominated the oxygen-free world has been replaced by complex networks of oxidation and reduction reactions that create new pathways for energy flow and nutrient cycling. These new chemical cycles are more complex and more energetically efficient than their anaerobic predecessors, supporting larger and more diverse biological communities. The evolution of aerobic bacteria has created entirely new types of ecological relationships and food webs that were impossible in the purely anaerobic world. Aerobic bacteria can break down complex organic molecules that anaerobic bacteria cannot fully utilize, creating new energy sources and nutrient cycles that support additional levels of biological complexity. The waste products of aerobic metabolism become resources for other organisms, creating intricate webs of interdependence that stabilize and enhance ecosystem productivity. The global temperature regime has been affected by the atmospheric changes accompanying oxygenation. The greenhouse gases that maintain the warm conditions of the early Earth, particularly methane, are gradually oxidized and removed from the atmosphere by the increasing oxygen concentrations. This leads to a slow, cooling trend that affects climate patterns worldwide and creates new environmental challenges for all forms of life. The cooling climate drives changes in ocean circulation patterns and creates new types of environmental variability that affect the distribution and evolution of marine organisms. Some regions become too cold to support the thermophilic bacteria that dominated the early warm seas, while other areas develop new temperature niches that can be colonized by cold-adapted bacterial lineages. The ice ages that will characterize much of Earth's later history begin to make their first appearance as the cooling climate allows ice sheets to form on the continents. These early glaciation events are relatively mild compared to later ice ages, but they represent the beginning of a new type of climate variability that will profoundly influence the evolution of life for billions of years to come. The continental surfaces, which were largely barren during the early phases of Earth's history, begin to show the first signs of significant biological colonization. The protection from ultraviolet radiation provided by atmospheric ozone, combined with the new metabolic capabilities of aerobic bacteria, allows life to begin exploring terrestrial environments that were previously too hostile for biological activity. The early colonization of land proceeds slowly and cautiously, with bacterial communities establishing themselves in protected environments such as moist soil layers, rock crevices, and the margins of freshwater bodies. These pioneering terrestrial communities face challenges that are completely different from those encountered in aquatic environments: extreme temperature variations, desiccation stress, and limited access to nutrients and energy sources. The terrestrial bacterial communities that emerged during this period develop remarkable adaptations for survival in the harsh conditions of early land environments. They evolve enhanced stress tolerance mechanisms that allow them to survive extreme temperature fluctuations and periods of desiccation. They develop new metabolic pathways that can extract energy and nutrients from the limited resources available in terrestrial environments. The establishment of terrestrial life creates new feedback loops between biological and geological processes that further accelerate the transformation of Earth's environment. Bacterial communities on land enhance the weathering of rocks and minerals, releasing new nutrients into rivers and streams that eventually reach the oceans. They also begin to modify soil chemistry and create the first primitive soil ecosystems that will eventually support more complex forms of terrestrial life. The deep ocean environments, which served as refuges for anaerobic life during the early phases of oxygenation, begin to experience their own transformations as oxygen slowly penetrates into even the deepest water masses. This process takes millions of years and proceeds very gradually, allowing deep-sea anaerobic communities time to adapt or retreat to even more protected environments. Some deep-sea environments develop complex chemical stratification, with aerobic conditions in the upper layers and anaerobic conditions in the deeper layers. These chemically stratified environments support diverse communities that include both aerobic and anaerobic bacteria, creating some of the most complex and sophisticated ecosystems on the planet. The mineral resources of the Earth begin to change as oxygen-driven weathering processes create new types of or deposits and mineral formations. The oxidation of sulfide minerals creates new sources of sulfate that affect ocean chemistry and provide new energy sources for sulfate-reducing bacteria. The weathering of silicate rocks accelerates under oxidizing conditions, affecting the availability of trace nutrients and altering the chemical composition of seawater. As you float in these transformed waters, surrounded by the complex communities of aerobic and anaerobic bacteria that now populate the ancient seas, you can appreciate the incredible journey that life has taken during the Great Oxygenation Event. What began as a simple innovation in bacterial photosynthesis has cascaded through every aspect of Earth's environment, creating a world that is fundamentally different from the one where this journey began. The warm waters around you now support a diversity of life that far exceeds anything that existed in the purely anaerobic world. Aerobic bacteria exploit the abundant oxygen to power highly efficient metabolic processes, while anaerobic bacteria persist in protected refuges where they maintain the ancient traditions of oxygen-free life. The interaction between these two great biological traditions creates a richness and complexity that demonstrates the incredible creativity of evolution when faced with environmental challenges. The planetary transformation that you have witnessed represents one of the most important events in the history of life on Earth. The Great Oxygenation Event created the chemical and environmental conditions that would eventually allow for the evolution of complex multicellular life, including all the familiar plants and animals that populate the modern world. Yet this transformation was accomplished through the patient, persistent work of microscopic bacteria over hundreds of millions of years, demonstrating that even the most profound changes in Earth's history unfold through processes that are fundamentally peaceful and gradual. The gentle currents that move through these oxygenated waters carry with them the chemical signatures of a world that has learned to accommodate both ancient and modern forms of life. The forgotten war between oxygen and anaerobic life has reached a peaceful resolution, with each side finding ways to thrive in a world that has been enriched by their long struggle and ultimate cooperation. As you continue floating through these transformed waters, now hundreds of millions of years into the Great Oxygenation Event, you begin to sense that every profound transformation comes with its own subtle costs and consequences. The victory of oxygen-producing life has been complete and transformative, creating a world that pulses with new energy and possibilities. Yet this triumph has also brought with it changes that would have been unimaginable to the simple bacterial communities that first began producing oxygen in the ancient seas. The most immediate consequence of the oxygen revolution has been what scientists would later call the first Great Extinction Event in Earth's history. Though the word extinction perhaps carries connotations too harsh for the gentle, gradual process that has unfolded over geological time. This has not been a sudden catastrophe or violent upheaval, but rather a slow fading away of lineages that could not adapt to the transformed chemical environment of an oxygenated world. Many of the bacterial species that once dominated the oxygen-free seas have simply disappeared, their populations declining gradually over millions of years as their preferred habitats became increasingly scarce and their competitive position deteriorated relative to more oxygen-tolerant organisms. The loss of these ancient lineages represents the end of billions of years of evolutionary experimentation and refinement, the quiet closing of biological chapters that will never be written again. Yet even this loss has occurred with a gentleness that characterizes all the transformations you have witnessed. The disappearing species have had millions of years to find refuges, to develop adaptations, or to evolve into new forms better suited to the changing world. Many lineages that seemed destined for extinction have persisted by retreating to specialized environments or developing unexpected innovations that allow them to survive in the new oxygen-rich world. The cooling climate that has accompanied atmospheric oxygenation represents another significant consequence of the oxygen revolution. The methane that once helped maintain Earth's warm, greenhouse climate has been largely oxidized and removed from the atmosphere, leading to a gradual cooling that affects every aspect of the planet's environment. This cooling has not been sudden or extreme, but rather a gentle shift toward temperatures that are more variable and, on average, somewhat cooler than the stable warmth of the oxygen-free world. The climate cooling has created new environmental challenges that affect both aerobic and anaerobic organisms. Some bacterial communities that evolve in the consistently warm conditions of the early Earth find themselves struggling to adapt to the increased temperature variability and generally cooler conditions. Others discover that the cooler temperatures actually favor their particular metabolic processes, leading to unexpected expansions in their populations and geographical ranges. The ice ages that begin to punctuate Earth's climate during this period represent entirely new types of environmental challenges that life has never faced before. During glacial periods, vast areas of the ocean freeze over, creating barriers to the movement and mixing of marine organisms. The formation of ice sheets on land locks up enormous quantities of water, causing sea levels to drop and exposing new areas of seafloor while eliminating other marine habitats. These climatic fluctuations create rhythms of environmental change that operate on timescales of thousands to millions of years, much longer than the life cycles of individual organisms, but short enough to create significant evolutionary pressures. Life must develop new strategies for coping with environmental variability, including enhanced dispersal abilities, broader environmental tolerances, and more flexible metabolic systems. The chemical cycles that govern life on Earth have become far more complex and interconnected as a result of the oxygen revolution. While this complexity creates new opportunities for biological innovation and specialization, it also makes the entire system more vulnerable to disruption. Small changes in one part of the global chemical system can cascade through interconnected pathways and create large effects in seemingly unrelated parts of the biosphere. The increased chemical complexity of the oxygenated world creates new types of pollution and environmental contamination that were impossible in the simpler chemistry of the oxygen-free Earth. Some of the waste products of aerobic metabolism are toxic to anaerobic organisms, creating localized zones of chemical contamination that can persist for extended periods and affect entire communities of sensitive bacteria. The enhanced weathering of rocks and minerals under oxidizing conditions releases new types of chemical compounds into the environment, some of which are beneficial to life, while others create new forms of chemical stress. The balance between beneficial and harmful chemical inputs becomes a constant challenge that requires ongoing evolutionary adaptation by all forms of life. The success of photosynthetic bacteria has created its own environmental problems as these organisms become so abundant and productive that they begin to significantly affect global chemical cycles. The massive production of organic matter by photosynthetic communities can lead to oxygen depletion in some areas as decomposition processes consume oxygen faster than it can be replenished. These oxygen-depleted zones become temporary refuges for anaerobic bacteria, but can also become sites of environmental stress for aerobic organisms. The accumulation of organic matter in sediments creates new types of geological formations that can affect long-term environmental stability. Large deposits of organic-rich sediments can become sources of chemical instability if they are later exposed to oxidizing conditions through geological processes such as uplift or erosion. The evolution of complex aerobic metabolisms has increased the energy flow through biological systems, but it has also increased the rate at which resources are consumed and waste products are generated. The faster pace of biological activity in the oxygenated world creates new pressures on resource availability and waste disposal that require ongoing adaptation by all organisms. Some bacterial communities find themselves caught in evolutionary arms races as the increased energy availability from aerobic metabolism allows for more rapid evolution and more intense competition between different lineages. These competitive pressures can drive rapid evolutionary change, but can also lead to the extinction of less competitive species. The increased metabolic efficiency of aerobic organisms allows them to extract more energy from available resources, but also means that they generate more waste heat and other byproducts that can affect local environmental conditions. The thermal pollution created by highly active aerobic communities can alter local temperature regimes and affect the distribution of temperature-sensitive organisms. As you drift through these ancient waters for the final time in your long journey through Earth's most profound transformation, you begin to understand that the story you have witnessed extends far beyond the immediate participants in this forgotten prehistoric war. The consequences of the Great Oxygenation Event ripple forward through billions of years of subsequent evolution, shaping every aspect of life that will ever exist on this planet, including the very air you breathe and the biological processes that sustain your own existence. The most fundamental legacy of the oxygen revolution is the establishment of the chemical foundation for all complex life on Earth. The aerobic metabolism that evolved during this ancient transformation provides the energy that powers every plant, animal, and fungus that has ever lived. The efficient energy extraction made possible by oxygen-based respiration is what allows for the evolution of large, complex organisms with sophisticated tissues, organs, and behaviors that would be impossible to sustain with purely anaerobic metabolism. The atmospheric oxygen that accumulates as a result of billions of years of photosynthetic activity creates the ozone layer that protects Earth's surface from harmful ultraviolet radiation. This protection opens up entirely new environments for biological exploration, allowing life to colonize land surfaces, shallow waters, and other areas that were previously too dangerous for biological activity. Without this protective atmospheric layer, the rich diversity of terrestrial life that characterizes the modern world would never have been possible. The oxygen-rich atmosphere also enables the evolution of fire, a phenomenon that becomes an important ecological force in terrestrial environments. The ability of organic matter to combust in the presence of oxygen creates new pathways for nutrient cycling and habitat modification that profoundly influence the evolution of land-based ecosystems. The relationship between life and fire becomes a complex dance of adaptation and coevolution that shapes the development of forests, grasslands, and other terrestrial communities. The chemical cycles established during the Great Oxygenation Event continue to govern the functioning of modern ecosystems. The carbon cycle, nitrogen cycle, sulfur cycle, and other biogeochemical processes that sustain contemporary life all bear the imprint of innovations first developed by bacterial communities responding to the challenges of an oxidizing world. These ancient chemical pathways provide the foundation for all subsequent biological complexity and diversity. The evolutionary innovations developed during the oxygen revolution, including aerobic respiration, antioxidant systems, cellular compartmentalization, and oxidative metabolism, become part of the genetic toolkit that life draws upon for all future evolutionary experiments. These innovations are preserved and modified by countless subsequent lineages, contributing to the evolution of everything from photosynthetic plants to large brain mammals. The refuges where anaerobic bacteria retreated during the oxygen catastrophe continue to support thriving communities of ancient organisms even in the modern world. Deep-sea hydrothermal vents, oxygen-free sediments, and other anaerobic environments maintain ecosystems that are direct descendants of the communities that first learned to survive in an oxidizing world. These modern anaerobic communities provide living windows into the ancient past and continue to contribute essential services to global ecosystems. The geological formations created during the Great Oxygenation Event, particularly the banded iron formations, become some of the most important mineral resources on Earth. The iron ore deposits formed by ancient bacterial activity provide the raw materials for human civilization, supporting the development of agriculture, industry, and technology. In this way, the metabolic activities of ancient bacteria continue to influence human society billions of years after their original formation. The patterns of environmental change established during the oxygen revolution create templates for understanding how life responds to global environmental transformations. The strategies developed by ancient bacteria for coping with changing atmospheric chemistry provide insights that are relevant to understanding how modern ecosystems might respond to contemporary environmental changes. The gradual, patient pace of the Great Oxygenation Event demonstrates that even the most profound environmental transformations can occur through processes that allow lifetime to adapt and evolve appropriate responses. This provides important perspectives on the resilience and adaptability of living systems when faced with environmental challenges. As you float here in these ancient waters, now fully transformed from their oxygen-free origins into something approaching the chemical composition of modern seas, you can appreciate the remarkable journey that life has taken over the billions of years encompassed by this transformation. What began as a simple innovation in bacterial metabolism has cascaded through every aspect of Earth's environment, creating a world that is fundamentally different from the one where this story began. The warm waters around you now pulse with the complex rhythms of a fully oxygenated biosphere, supporting communities of organisms that span the entire range from ancient anaerobic bacteria, maintaining billion-year-old traditions, to highly evolved aerobic organisms that push the boundaries of biological possibility. This diversity represents the ultimate resolution of the forgotten prehistoric war, not the victory of one side over another, but the creation of a world rich enough to support both ancient and modern forms of life. The gentle currents that carry you through these transformed seas bear the chemical signatures of countless biological innovations, evolutionary experiments, and adaptive strategies that have been tested and refined over geological time. Every molecule of oxygen in the water around you represents the metabolic activity of photosynthetic organisms, while every trace of anaerobic byproducts speaks to the persistence of ancient lineages that have maintained their traditions despite the fundamental transformation of their world. As your journey through this forgotten war draws to a peaceful close, let yourself be carried by the gentle rhythms of these ancient waters, feeling the weight of billions of years of evolutionary history in every breath, every heartbeat, every thought. The oxygen revolution that you have witnessed created the chemical and biological foundation for all complex life, including the miraculous processes that sustain your own consciousness and allow you to contemplate the deep history of the world around you. Rest now in the knowledge that you have witnessed one of the most important chapters in the story of life on Earth, a transformation so profound and far-reaching that its consequences continue to shape every aspect of the living world. The forgotten prehistoric war between oxygen and anaerobic life has been resolved not through conquest or defeat, but through the patient work of evolution, creating a world diverse and resilient enough to honor both ancient traditions and revolutionary innovations. Let the warm waters of these transformed seas carry you into peaceful sleep, knowing that the air you breathe, the energy that powers your cells, and the complex chemistry that sustains all life on Earth are the direct inheritance of the bacterial heroes whose patient struggle you have been privileged to witness. In their quiet victory, life found a way not just to survive, but to flourish in ways that surpass even the most optimistic dreams of those simple organisms that first began releasing oxygen into the ancient seas so many billions of years ago. Sleep well, carried by currents that connect you to the deepest roots of life itself, knowing that you are part of an unbroken chain of existence that stretches back to those ancient bacterial communities and forward to possibilities that have yet to unfold in the continuing story of life on Earth.